Hello, I'm Mr. McBrien. This is TEJ3M LEDs. So, we've already talked about conductors and how Ohm's law describes how current flows through them. Specifically, current's equal to voltage or potential divided by resistance. So this simple relationship determines the current that flows through a conductor. It's worth noting that there are components that don't behave according to Ohm's law. So, as the title would imply, LEDs are one of these. Before we go any further, let's quickly go through the history of light-emitting diodes. So, the first red LED was produced in 1962, and it had some interesting characteristics. It had very low power consumption. The light that came out of it was very high intensity, it was durable, and it was monochromatic, single color. So it started out with red, and then yellow and other colors followed afterwards. Now the nature of these light-emitting diodes made them very useful for indicators and various mobile functions. And they're useful right through to today, 68 years later, and useful enough for us to dedicate one lesson to them. Now, to understand how diodes and light-emitting diodes are different from normal conductors, first off, we can start with this simple circuit that I constructed and the current that I measured from it. So we have the current in amps measured as a function of the potential as we change the potential in this circuit. And we see a simple relationship. The current goes up as we increase the potential, as we would expect. Now, LEDs behave very differently. So if we design an LED circuit where we have a light-emitting diode attached to our potential source and we start varying the potential, we see a very, very different profile. So we start off with zero current all the way through until we hit about 2 volts, and then the current shoots up very, very quickly. So this is far from a linear relationship. Now, as we're discussing this, we can start by first talking about the idea that we can increase the potential on this component and we see no current. It's like the voltage isn't even there. So diodes and LEDs exhibit zero current below a certain voltage. We call the voltage that we have to overcome the forward voltage or the forward voltage drop. So when we put a red LED in a circuit, it's like 2 volts just disappears. Try a blue LED, well, 3 volts will just disappear. So this drop in effective voltage is fairly predictable for a given component. Incidentally, a simple diode will have, a silicon-based diode will have about 0.6 or 0.7 forward voltage drop. But that doesn't explain why. Okay, so to understand why, we need to get into the physics of conductivity, which we haven't really done too much as yet. But in a normal conductor, electricity will flow when electrons move from one atom to another. And this is a relatively easy process because electrons are on the outer layer of the atom. We don't have to dig deep into it to pull one of those electrons off. And it's also an easy process because metals don't hold on to those electrons very tightly. It's one of the characteristics of metals. Now, but if we want to see some different characteristics, we can design different kinds of conductivity. So we can design what we call semiconductors by taking impurities onto a wafer and form regions of different electrical conductivity. So we can have negatively charged semiconductors or N-type semiconductors where that impurity will contribute a free electron if we put a little energy in to get it off. And we can have positively charged semiconductors where there's what's called a hole, a place for an electron to be. And that has, no great surprise, a positive charge instead of negative. Now when it comes to current in semiconductors then, the p-type, the current moves through these holes, moving from one atom to the next, or one matrix to the next. And in n-type semiconductors, the current flows via those electrons. If we want to make a diode, we just need to connect the p-type semiconductor to the n-type semiconductor. And so this is a cartoon of it right here, where we can see holes moving in one direction, obviously from the positive side of the circuit, and electrons moving in the opposite direction in order to move charge. And this is like the definition of current when you think about it, charge moving. So in a diode then, electrons flow one way, holes flow the other. And the energy that we need, that we talked about, to generate those holes or to free those electrons, well, that's the potential that we found missing when we were measuring our potential voltage drop. Now, one more note about that. When the electrons eventually find a hole, well, they go from being high energy to being very low energy. They go into their happy place. So the electrons reach the holes at the junction between the p-type and the n-type semiconductor. They go back down in energy level. And you might remember the first law of thermodynamics. Energy can't be created or destroyed. It just changes form. So our energy goes from being this electrical potential that's holding that electron up in that high free energy state. Well, when it drops down, that energy associated with the forward voltage gets converted into light. And that's why it's a light emitting diode. Okay, so we've figured out a couple of mysteries then today about why LEDs behave the way they do. We've explained that crazy forward voltage, and along the way we've explained the fact that it emits light. But there's more to it than that. We need to talk about what happens when we apply a negative potential across a diode. So if we apply a negative potential across a conductor, no big deal at all. What happens? We get negative current. So we simply push the current in the opposite direction. Something different happens in that circuit that I designed with my red LED. In fact, as we move our potential into the negative realm and further negative, no current occurs. So the current remains at zero. And this even applies after we've gone past our forward voltage. So this will go down even further to lower and lower or more and more negative voltages. We still see no current. So why is this then? Well, in order to understand this, we need to dig a bit deeper into that conductivity in a semiconductor. So here's a different cartoon of a PN semiconductor with our positive holes moving towards the junction and our negative electrons moving towards the junction. And when we apply the potential in that direction, no big deal. The electrons move towards their happy place, towards the holes. And at that junction, then we see energy get released in the form of light, and the current can continue to flow. When we reverse the potential, called reverse biasing, our electrons try to move in the opposite direction. And our holes move in the opposite direction. Well, here's the weird thing about that. The electrons, the positive semiconductor can't produce any electrons. Similarly, the negative semiconductor can't produce holes. And so we get this depletion region, and there's nothing that we can do to allow current to flow once that depletion region has been created. And this is the whole basis of that one-way current flow. We reverse the bias on a diode, there's no current. So this leads us to the idea of what's called a polarized component. LEDs have an anode and a cathode, the anode being the positive. Notice that it's the longer leg of our LED. Our negative cathode is the shorter leg. If you have very sharp eyes, you'll notice there's also a flat spot on the plastic here. So components that have an anode and a cathode are called polarized. And whereas with resistors, we can simply slap them into our circuit, not worrying about which direction the current's flowing, we have to be more careful with our polarized components. Okay, so diodes then provide us with this one-way valve for flow of charge. We can control the flow of charge, allowing it to go in only one direction. And each of these, by the way, a given diode on its data sheet, you'll be able to find the forward voltage drop. The symbols for these things, the LED we've already seen. It has arrows that represent the light beams coming off of it, but also it incorporates this symbol of a diode. So let's summarize then quickly diode behavior. So an ideal diode, when it's forward biased, will have a current greater than 0. The voltage across it will be essentially 0, and it'll look like a short circuit. When it's reverse biased, the current should be 0. The voltage across it should be less than 0, and it will behave like a switch that is open. Okay, so there is something else we need to consider when we're looking at LEDs, and that's that they need protection from too much current. Above our forward voltage, they behave like a wire, like a short circuit. But unfortunately, LEDs can't handle very high currents at all. We target about 20 milliamps for our LEDs that we use. And anything above about 0.04 amps, 40 milliamps, will burn them out. So in order to reduce the current through the LEDs, they won't produce any resistance themselves. We have to wire them in series with a resistor. So here's a cartoon of the kind of simple design that we can create with our LED connected to positive through the resistor back down to our battery. Okay, now you might say to yourself, okay, these sound like really complicated circuits. They're pretty simple to predict what's going on. When we go to calculate the current through one of these, we simply subtract the forward voltage drops. We assume the LED has 0 resistance, and then we look for any series resistors to determine our current. Let's look at an example. So here's that cartoon circuit with a potential source, a resistor, and an LED. Now if this is a blue LED, a 5-volt potential source, and a 470 ohm resistor, we need to be able to calculate the current. Alright, so we're given a forward potential of 5 volts. Our voltage drop will be 3 volts because it's a blue LED, and our resistance is 470 ohms. We need to find the current. Well, our new equation here is simply subtracting the forward voltage drop from the applied potential divided by the resistance. So 5 volts applied minus 3 volts forward voltage drop on the LED divided by 470 ohms, by my count, gives us about 4 milliamps. Safe enough for an LED. What about when we put the LEDs in series? Well, when we put them in series, we need to actually add the forward voltage drops for these components. So with 3 red LEDs in series, we see a forward voltage of 3 times 2 volts, or 6 volts. The rest of the calculation is the same. We substitute in 5 volts applied minus 6 volts divided by 470 ohms gives us negative 0.02 amps, or negative 2 milliamps. Well, wait a second. Negative? Well, we talked about previously that just means the current's going to flow in the opposite direction. Well, we need to remember these are diodes. Current can't flow in the opposite direction. In fact, what will happen is we'll see zero current here. So we need to keep in mind that anytime the forward voltage drop exceeds the potential available from the potential source, we'll see zero current. So this is in fact the answer to what's the current on this question is in fact 0 amps. And you should be able to produce this on a test or quiz. Okay, speaking about units, no new units to cover today on LEDs. The maximum current though through an LED is about 40 milliamps. We target 20 milliamps. The forward voltage for an LED is between 2 and 3 volts depending on the color of the LED. 0.6 or 0.7 volts for a silicon diode, and other ones you'd need to look up. Okay, key points for today then. Diodes don't behave like conductors. They're semiconductors and they behave in a super different way than your standard conductors. One of the aspects is that current can only flow one way. Another aspect is that we have a forward voltage that is lost. Having said that, the resistance of diodes is very close to zero once that forward voltage is overcome. LEDs are efficient light sources, but we've got to protect them from excessive current with a series resistor. Which one depends on the situation involved. Okay, for your homework then, please complete the LED worksheet and go ahead and access LJ Create for calculating the resistor value for an LED lamp circuit. Should help you with your worksheet as well. Thanks very much, and have a great night.